Good morning. Today we are going to discuss one corollary, and the statement of the corollary is let E subset of F closure is a splitting field over F. Then every irreducible polynomial f of x having a 0 in E splits in E. And just to recall the definition of splits in E. A polynomial f of x belongs to f of x splits in E if it factors into product of linear factors in E of x. Okay, in E of x. A polynomial must be in f of x and it is factors into product of linear factors in E of x. Then we call a polynomial f of x in f of x splits in E. So here we are saying if E is a splitting field over F, then every irreducible polynomial in f of x having a 0 in E splits in E. That polynomial you can factorize. Okay. Okay. Now for the proof, let E subfield of F closure be a splitting field over F, and let G of x be an irreducible polynomial in f of x having a 0 alpha in E. And we have to prove this polynomial G of x is splits in E. That means G of x you can write as a product of linear factors. Okay. Let beta be any 0 of G of x in F closure. Then the conjugation isomorphism theorem, by conjugation isomorphism theorem, there is a unique isomorphism psi alpha beta from f of alpha on to f of beta, leaving f fixed. Okay, because alpha is a 0 in E means alpha is algebraic over f. Okay, similarly beta is a 0 means beta is algebraic over f. Therefore, we can define a conjugation isomorphism. Okay. Then by corollary, 7.2 we get this number, you can correct. We get an isomorphism to or on to as an on to isomorphism of F closure leaving F fixed, and it to induces an automorphism on E. That means by that theorem, this conjugation isomorphism psi alpha beta you can extend to an isomorphism of F closure leaving F fixed. Okay, and by this theorem, this tool induces an automorphism on E. So tau of an element of E is an element of E. That means tau alpha belongs to E. That means psi alpha beta of something, some element. You can write some psi alpha beta of alpha belongs to E. This implies beta belongs to E. Therefore, if you take any beta belongs to E and which is a 0 of G of x, then that 0 also belongs to E. Therefore, all zeros of G of x in F closure is in E. Then every irreducible polynomial in f of x having a 0 in E has a linear factorization in E of x, because every 0 of f of x is in G of x in F closure is in E. If you consider this polynomial x square plus 1 equal to 0 in C, the zeros are I and minus I. That means x minus I into x plus I. We can write this on just because I belongs to C. If you consider this in R, then this cannot be factorized. Therefore, here the statement is all the zeros of G of x in F closure is in E. All zeros belongs to E. So we can write that polynomial as a product of its roots. Okay. Thus, every irreducible polynomial in f of x having a 0 in E has a linear factorization in E of x. That is, G of x splits in E. Okay. Now, I I think this is repeated here. Okay, there is no need of this portion. It's the same as earlier. Okay. I think this part is here actually. Both are same. Proof is same, but in this proof, here this term already. Okay. To of an element, this you can add. To of an element belongs to E. To alpha belongs to E implies I alpha belongs to E implies beta belongs to E. Okay. And G of x plus in E, hence the corollary. You can add these two still. Okay. Both proof is same. Okay. Now next is one corollary and that we will discuss in our next class. Okay. So before that, now we are going to discuss one problem. Find the splitting field of x cube minus 2 over q. Find the splitting field of x cube minus 2 over q. This is very important. Okay. It's very important. For this, what we have to do? We have to find splitting field of x cube minus 2. That means that splitting field must be smallest field containing all the root of this polynomial. Okay. And also contain q. So before this, first we find roots of the polynomial x cube minus 2. X cube minus 2 equal to 0 implies x equal to plus or minus cube root of 2. Cube root of it 2 is the real 0 of this polynomial. Therefore, this you can factorize this. Okay. So x minus 2 raised to 1 by 3 into this one. Okay. How we get this one? This term. How we get this term? Just write like this: x cube minus 2 divided by x minus 2 raised to 1 by 3. So here x square, x cube minus 2 by 3 x square. Subtracting we get 2 by 3 x square minus 2 by 3 x, so sorry, 2 raised to 1 by 3 x. So 2 raised to 1 by 3 x square minus 2 raised to 2 by 3 x. So if you subtract this, 2 raised to 2 by 3 x minus 2. So here plus 2 raised to 2 by 3. So 2 raised to 2 by 3 x minus 2 raised to 3 by 3, that is 1, 0. So this is the fact. Okay. So now this equal to 0 implies what? This is a quadratic polynomial. Okay. So x is equal to, you use minus b plus or minus. And finally we get the value as this one. 2 raised to 1 by 3. Okay. Now the zeros of x raised to 1 by 3 minus 2 are 2 raised to 1 by 3. 2 raised to 1 by 3 into this one. Okay. Here we go. Now hence the splitting field of x cube minus 2 or q is the smallest subfield of q closure containing q and all the zeros. So 2 raised to 1 by 3 and this term. In q, okay, we have to find smallest field. So if you consider q, we get only rational numbers. So we have to find the smallest subfield of q containing q 2 raised to 1 by 3 and this one. Okay. So the field is q. it must contain 2 raised to 1 by 3. So it is must be, you can write like this. But if you write like this, then this term is missing. Okay, so we can write this as q of 2 raised to 1 by 3 comma I root 3. Okay, therefore splitting field of x cube minus 2 over q is q of cube root of 2 I root 3. Okay, q of cube root of 2 comma I root 3. Okay, now next is find the degree of the splitting field E of x cube minus 2 over q. We have to find degree of, okay, degree of the splitting field. So here we already find splitting field. Now we have to find degree of q of cube root of 2 comma I root 3 over q. Okay, so for this consider x cube minus 2 over q, and this is the splitting field. We have q is a subfield of q of I root 3 is a subfield of q of I root 3 of 2 raised to 1 by 3. Okay, so we have to find this one. Okay, but this you can write as q of I root 3 of 2 raised to 1 by 3 over q of I root 3 into degree of q of I root 3 over q. Okay, so now alpha equal to I root 3 implies alpha square minus equal to minus 3, alpha square plus 3 equal to 0. Note that x square plus 3 is an irreducible polynomial in q of x. Therefore, irreducible of I root 3 over q is equal to x square plus 3. Okay. Hence, degree of irreducible of I root 3 over q is equal to 2. Degree of q of I root 3 over q equal to 2. Okay, so if you take now, we have to find this over this. Now if you take alpha equal to 2 raised to 1 by 3, alpha cube equal to 2, this implies alpha square minus 2 equal to 0. That means x cube minus 2 is an irreducible polynomial in q of I root 3 of x. Okay, therefore q of irreducible of 2 raised to 1 by 3, q of I root 3 is equal to x cube minus 2 and its degree is 3, which implies degree of this one equal to 3. Therefore, degree of this one equal to 3 into 2, which is equal to 6. Now, I am giving one problem as homework. Find the degree of q of cube root of 2, comma I, comma root 3, okay, over q. Okay. So from this, degree of this one is equal to 12 and degree of this over this equal to 6. From this it is clear that these two fields are not same. Here this is I root 3. This is I comma root 3. Okay. What about I comma root 3? Degree of this is 12. We have to, this also contain root 3 root 2 raised to 1 by 3 I root 3, but splitting field means polynomial field of degree, smaller degree. That's why we have choose this. Okay, this is the splitting field. Okay, that's all for today's class.